Most of the universe is not made of stars, planets, or glowing galaxies. It is made of distance, silence, and vast regions so empty they almost seem impossible. These are cosmic voids, the largest quiet spaces ever discovered, stretching across hundreds of millions of light years. But they are not truly empty, and they may reveal how the universe grows on its biggest scales. If this kind of deep space documentary is enjoyable, please like the video, subscribe to the channel, and stay for the full journey. Across the observable universe, matter is not spread evenly. On the largest scales, it forms a pattern of bright knots, long threads, and wide, dim spaces between them. This pattern is called the cosmic web. It has no preferred center. It is the long-term outcome of gravity acting on tiny differences that exist in the early universe. The widest view begins with distance and time. Light from a distant galaxy travels for billions of years before it reaches an observer. So a deep view of the sky is also a view into earlier eras. When many galaxies are gathered into one map, their positions show a clear structure. They collect into groups and clusters, where hundreds to thousands of galaxies share a common gravitational environment. Clusters are connected by filaments, elongated bridges of galaxies and dark matter that stretch for tens to hundreds of millions of light years. Between filaments lie broader walls, flatter regions where matter remains above average but less concentrated than in the brightest knots. Between these boundaries lie the largest volumes, regions with far fewer galaxies where the web thins and the sky appears quiet. This architecture is measured rather than imagined. Galaxy surveys record positions across wide areas and estimate distances from redshift. The stretching of light by cosmic expansion. When these positions are plotted in 3 dimensions, the web appears as a foam-like arrangement of dense boundaries surrounding large, low-density interiors. No single survey covers the entire sky with the same depth, yet the broad pattern repeats across independent maps. Dense nodes stand out because they contain many luminous galaxies. Filaments and walls emerge because galaxies align in chains and sheets rather than scattering uniformly. The emptier regions emerge because long lines of sight pass through volumes with very few traces at all. The web is also a map of invisible matter. Most of the mass in the universe is dark matter, which does not emit or absorb light in ordinary ways. Its presence is inferred through gravity, through how galaxies move, how clusters hold hot gas, and how light is bent along the line of sight. In the cosmic web, dark matter provides the main scaffolding. Ordinary gas falls into its gravitational valleys, cools, and forms stars, creating galaxies where the dark matter density is high enough to gather and hold baryonic matter, the ordinary matter of atoms built from protons and neutrons. In this widest view, galaxies are visible markers placed on a broader mass distribution that extends beyond starlight. The web's large-scale form reflects a balance between growth and expansion. Gravity amplifies differences, pulling matter into denser regions and draining it from less dense regions. Expansion stretches space and lowers average density, slowing the rate at which structures grow. Over cosmic time, these tendencies produce a hierarchy. Regions that begin slightly denser tend to become nodes and clusters. Regions that begin slightly less dense tend to become broad underdense volumes. The boundaries between them sharpen as matter flows from interior low-density regions toward the filaments and nodes that surround them. Clusters sit at intersections of filaments, where flows converge. They are the clearest landmarks in a large-scale map because their galaxy density is high. They also contain large reservoirs of thin, extremely hot plasma, and they act as strong gravitational lenses. bending the light of more distant galaxies. These measurements reveal that most cluster mass is not in stars. It is in dark matter that extends well beyond the visible galaxies. Filaments are more delicate than clusters, yet they are widespread. They can be traced by chains of galaxies and by weak gravitational lensing, which reveals slight coherent distortions in the shapes of background galaxies. In some cases, thin gas in filaments leaves faint absorption features in the spectra of background sources. Even when the gas is hard to detect directly, the web-like arrangement of galaxies and lensing mass shows that filaments are not empty corridors. They are the channels through which matter moves toward the densest nodes. Walls are broader and less sharply defined. In large surveys they appear as extended sheets of galaxies, long structures that can span hundreds of millions of light-years. Their existence is consistent with anisotropic collapse, where matter first contracts along one direction to form a sheet and later along another direction to form a filament. These shapes are not perfect. They bend, fragment, and merge. Yet the overall effect is a network of boundaries that surround large interior regions. The wide low-density regions between these boundaries occupy most of the universe's volume. They are not holes in space. They are regions where the density of matter is below the cosmic average and where galaxies are sparse. They contribute less to total mass than clusters and filaments, yet they dominate the amount of space between the luminous structures. In a map, these interiors are defined indirectly. When filaments and walls appear as connected boundaries, the interior spaces become clear as the connected regions that remain. This larger-scale architecture is also dynamic. Galaxies follow the overall expansion of the universe while also moving under local gravity. These extra motions are called peculiar velocities. In clusters they are large because gravity is strong. Along filaments they tend to align with the structure, reflecting infall toward nodes. In broad low-density interiors they often point outward toward the surrounding boundaries, because the gravitational pull of denser regions draws matter away. Over billions of years, these slow flows sharpen the contrast between dense boundaries and low-density interiors. In this outer frame, the cosmic web provides a calm map of where matter gathers and where it thins. It shows that the largest empty-looking regions are part of the same gravitational story as the brightest clusters. The web sets the scale and the language for everything that follows a universe of structure drawn by dark matter, traced by galaxies, and shaped by long, quiet flows that make some regions crowded and leave other regions spacious. Even in the emptiest volumes, a thin presence of matter remains and the network stays connected across immense distances. Within the cosmic web, a void is defined by what is missing and by what remains. A cosmic void is a region where the density of matter is lower than average across a large volume. It is not an absence of space, and not a hole in the universe. It is a place where gravity has moved matter outward over long time, leaving behind a thinner mixture of dark matter, gas, and a small number of galaxies. The first step is to define density in a cosmological sense. The universe has an average density that can be described statistically. In any given region, the density can be higher or lower than this mean. A void is identified where the density falls below the mean by a significant fraction over a contiguous volume. This definition depends on scale. A small, underdense pocket inside a filament is not typically called a cosmic void, because it is not part of the large-scale foam-like structure. A void is usually discussed as part of the hierarchy of the cosmic web, bounded by filaments and walls and spanning tens to hundreds of millions of light-years. The word empty is used because voids look empty in galaxy maps. In a typical redshift survey, Clusters appear as bright knots of many points, filaments appear as chains of points, and voids appear as wide gaps. Yet the map shows galaxies, not mass directly. The absence of galaxies in a region is a strong clue that the region is underdense, but it is not a guarantee that it is devoid of matter. The same region can still contain dark matter and diffuse gas at levels that are simply hard to detect with ordinary starlight surveys. A void's boundary is also not a wall. It is a transition zone where density rises from below average inside the void toward above average in surrounding filaments and walls. In many cases, this transition is gradual. The void interior is not uniform either. Some voids have a relatively flat central region of low density. Others contain smaller filaments and small galaxy groups within them, a faint internal web sometimes called substructure. This makes a void less like a smooth bubble and more like a low-density landscape with gentle hills and sparse ridges. Because of this complexity, different methods of defining voids can produce different catalogues. One method finds the largest regions that can be filled with spheres that contain very few galaxies. Another method traces the density field and identifies basins in that field, regions that are local minima surrounded by ridges. Another method uses tessellation, dividing space into cells around each galaxy, and identifying large volumes where cells are unusually large, implying galaxies are far apart. Each method captures the same general phenomenon but draws boundaries in a different way. The scientific focus remains on the underlying idea, a large region where the matter density is significantly below average. The practical quantitative description of a void often uses the density contrast, the fractional difference between local density and the mean. A density contrast of -1 would mean complete absence of matter, which is not expected in standard cosmology. Real voids have density contrast that are negative but not extreme in that sense. They can be missing a large fraction of their matter relative to the mean, yet still retain some dark matter and some gas. In addition, density varies with radius. A typical void profile shows the lowest density near the center and a rise toward the edge, often with an overdense ridge just outside the nominal boundary where matter has accumulated. The presence of dark matter inside voids is a key part of the definition. Dark matter responds to gravity and participates in the growth of structure. In regions that begin slightly underdense, matter flows outward, reducing density further, yet the density does not drop to zero, because initial fluctuations are small and because matter is collisionless. Streams of dark matter can pass through one another without shock, smoothing and spreading. As the void expands, its interior becomes more uniform in relative terms, but it retains a background of dark matter. This background can still form small halos, gravitational wells that can hold gas and form small galaxies. The halos are fewer and less massive on average than those in filaments, which is why void galaxies are rare and tend to be smaller. Void galaxies provide an internal check on the definition. They are not common, but they exist. They tend to be isolated, with fewer close neighbours. Their star formation histories can differ from those in dense environments because their gas supply and their merger history are different. The existence of void galaxies shows that voids are not empty of structure. They're empty relative to the surrounding web, not empty in an absolute sense. The gas inside voids is even harder to see than galaxies. Most of it is ionized, meaning electrons are not bound to nuclei. Ionized gas does not emit much visible light at low density, so it is often detected indirectly through absorption lines in the spectra of background galaxies and quasars. These absorption features reveal that even low-density regions contain gas, and they show that the intergalactic medium has a complex temperature and ionization structure shaped by cosmic expansion, by ultraviolet radiation from galaxies and quasars, and by the slow heating that occurs when matter falls into filaments and shocks. A void is therefore a region defined by underdensity and by boundaries. It is a cavity in the cosmic web, but it is not a clean, hollow sphere. It is more like a basin surrounded by ridges, with a floor that is not flat and with a thin presence of matter throughout. The basin expands over time relative to the cosmic mean because its density contrast evolves. As the universe expands, the mean density drops everywhere, but within voids the density drops faster relative to the mean because matter continues to flow outward. This outward flow is an important part of what makes voids grow. In dense regions, gravity pulls matter inward and increases density. In underdense regions, the gravitational pull from surrounding overdensities dominates, and the net effect is a drift of matter away from the interior and toward the edges. In the language of cosmology, voids undergo expansion faster than the average expansion, because their lower gravity slows collapse and allows space within them to stretch more. This does not mean space itself is torn open. It means that the underdense region's volume grows relative to the mean, and its boundary moves outward in moving coordinates, the coordinate system that expands with the universe. The calm description of a void therefore includes three pieces. It is an underdense volume in the cosmic web, not a true emptiness. It has boundaries defined by surrounding filaments and walls, and those boundaries are broad transition zones rather than sharp shells. It contains dark matter and diffuse gas, and sometimes a small internal network of small halos and rare galaxies. Observations indicate that voids occupy most of the universe's volume, and that their density profiles and galaxy content are consistent with gravitational growth from small initial fluctuations. It remains uncertain how best to define void boundaries in a way that is uniform across surveys and redshifts, because different algorithms and tracer populations can draw different edges on a continuous, complex density field. A void becomes visible when the sky becomes a map with depth. On the surface of the sky, galaxies are points scattered across a sphere. Patterns can be hinted by clusters of points and by broad gaps. Yet a true void is a three-dimensional volume. To see it, observers convert angular positions into distances and then reconstruct a distribution in which dense boundaries and quiet interiors appear as shapes in space rather than as accidents of projection. The main tool for this reconstruction is redshift. Light from a galaxy carries spectral features produced by atoms and ions. As the universe expands, wavelengths are stretched, shifting these features toward longer wavelengths by the same fractional amount. That fractional shift is called redshift, and it provides a measure of how much the universe has expanded since the light is emitted. In standard cosmology, redshift is related to distance, so it becomes a practical coordinate along the line of sight. A survey begins with imaging. Wide-field telescopes record large regions of the sky and detect many faint galaxies. The next step is to measure redshifts. The most direct method is spectroscopy. A spectrograph spreads a galaxy's light into a spectrum and reveals specific lines and breaks, allowing a redshift to be measured with relatively high precision. Spectroscopic surveys are costly, so they usually target a selected sample and may face practical limits in very crowded regions where not every galaxy can be observed. A second method uses photometric redshifts, inferred from brightness through several broad filters. This approach reaches far more galaxies, but distance estimates are less precise and structures are smeared along the line of sight. Once redshifts are measured, the survey becomes a three-dimensional dataset. Each galaxy has 2 angular coordinates and 1 distance-like coordinate. Converting redshift to distance requires an assumed expansion history, and the reconstructed positions are commonly expressed in comoving coordinates. A coordinate system that expands with the universe so that the large-scale web is not blurred by overall expansion. The resulting map is not a direct picture of mass, it is a picture of traces. Galaxies form in dark matter halos, and halos are more common in denser regions. This introduces bias, meaning the galaxy density contrast is not identical to the matter density contrast. In void interiors, galaxies can be missing even when some dark matter remains. The tracer choice matters as well. Bright, massive galaxies trace the densest regions strongly and leave voids looking emptier, while fainter or more actively star-forming galaxies can populate lower density environments and make void interiors appear less empty. Surveys therefore interpret voids as underdensities in the tracer field that correspond, in a modelled way, to underdensities in the underlying matter. Selection effects must be controlled. Many surveys are flux limited, detecting galaxies above a brightness threshold. Farther away, only brighter galaxies remain visible, so the observed number density declines with distance even in a uniform universe. If this effect is not corrected, it can mimic a void. Analysts handle this by constructing volume-limited samples where possible, choosing cuts that keep the sample complete out to a chosen range, or by weighting galaxies to account for the changing selection function. These steps trade depth for uniformity, but they make density comparisons meaningful and reduce the risk of confusing survey sensitivity with true structure. Survey geometry also matters. No survey has perfect coverage. The Milky Way blocks parts of the sky with dust and stars, and bright foreground stars create masked patches. Instrument footprints produce edges and holes. These gaps can imitate underdense regions unless they are included in the analysis masks and corrections. A standard check compares measurements against random point sets that follow the same selection and sky coverage, so that void identification is not driven by where the survey looks. Redshift space is not quite real space because galaxies have peculiar velocities, motions caused by gravity in addition to expansion. These velocities shift the observed redshift slightly. In dense regions, the effect can stretch structures along the line of sight. In underdense regions, it can mildly compress them. These distortions do not remove voids, but they can shift apparent boundaries and change measured contrasts. Many analyses either model these effects or use identification methods that remain stable under them. With the corrected 3-dimensional tracer field in hand, voids are identified by algorithms that search for low-density regions. Some methods place large empty or nearly empty spheres and merge overlapping ones into larger regions. Other methods reconstruct a smooth density field from the discrete galaxies and then locate basins, regions where density is lower than the surrounding ridges. In each case, a void is defined relative to the survey's mean density after correction, and the boundary is a transition where density rises toward filaments and walls. Reliability is tested through repetition and comparison. If the survey is split into independent subsets, the largest voids and the strongest surrounding structures remain broadly consistent. Overlapping surveys provide further checks, because the same region of space can be mapped with different instruments and selection strategies. Simulations are also used to build mock catalogues that pass through the same selection and masking, allowing void finders to be validated in controlled conditions and helping distinguish real underdensities from gaps created by sampling noise. In this way, galaxy surveys turn emptiness into a measurable object. A void is not a blank patch on the sky. It is a connected region in a three-dimensional map where the galaxy number density, after careful correction, falls below the mean over a substantial volume. The boundaries are traced by surrounding dense structure, and the interior is defined by sparse traces rather than by absence. Observations indicate that modern redshift surveys reveal a network of low-density regions that occupy much of the mapped volume, and that these regions persist across independent datasets and methods. It remains uncertain how much the smallest and least pronounced voids depend on tracer choice and algorithm settings, because at small scales sampling noise and peculiar velocities can blur the distinction between true underdensities and statistical gaps. Voids appear first as gaps, then as volumes, and finally as a family of shapes. Once a survey turns sky positions into depth, low-density regions become connected spaces with measurable size, measurable boundary structure, and a relationship to other voids nearby. In practice, no void is a perfect sphere and no void stands alone. The cosmic web is continuous, so the emptiest regions form a hierarchy with small cavities inside larger basins and with boundaries that merge and split depending on the scale at which the density field is examined. Size is the most immediate descriptor, yet it is not as simple as a diameter. A void has an irregular boundary and a complex interior, so analysts often reduce its extent to an effective radius. The volume of the void is measured from the region assigned to it by a void-finding method. Then that volume is converted to the radius of a sphere that would have the same volume. This effective radius allows comparison even when true shapes differ. It also allows a catalogue to be summarized by a size distribution. Observed void sizes span a wide range. Small voids can be comparable to the separations between modest galaxy groups, while the largest voids span tens to hundreds of millions of light-years across in co-moving scale. The exact range depends on the tracer population and the survey depth. A bright galaxy catalogue produces fewer tracers and therefore identifies larger empty regions, while a denser catalogue that includes fainter galaxies fills in some of the space and breaks large regions into smaller ones. For this reason, void size is partly a property of the underlying matter field, seen through a particular set of tracers and a particular smoothing scale. Shape is the second descriptor, often summarized through ellipticity. A void can be approximated as an ellipsoid, and the lengths of its principal axes can be estimated from the distribution of its volume elements. Many voids are elongated, either because surrounding filaments are arranged asymmetrically, or because several low-density basins overlap along one direction. Some are flattened where they press against a wall-like structure. These shapes reflect anisotropic gravitational evolution, where matter collapses more readily along some directions than others, leaving underdense regions to expand most where resistance is weakest. The boundary is a transition zone rather than a shell. Density typically rises from a low interior toward the edge, and in many cases a ridge appears just outside the nominal boundary, where matter has accumulated. Some voids are strongly compensated in the sense that their surrounding ridge is prominent, while others sit inside broader underdense landscapes with only a modest ridge. This difference affects the way flows behave. A prominent ridge can slow outward streaming near the edge, while a modest ridge can allow outflow to continue toward more distant structures. Hierarchy appears when voids are identified at multiple levels. The same region can contain a large underdense basin that holds smaller voids separated by faint internal filaments and small galaxy groups. Over time, smaller basins can merge as their separating ridges thin and as matter continues to move outward. This is often described as void-in-void growth, a gradual coarsening in which larger basins become more dominant in volume. There is also a contrasting case where a small underdensity is embedded within a larger overdensity. In that environment, the surrounding matter collapses and the small low-density pocket can be squeezed away rather than expanding into a lasting void. This explains why voids are not simply the negative images of clusters. Their survival depends on the larger-scale density around them, not only on their local minimum. The largest underdense complexes are sometimes called supervoids. The word is informal and depends on how connectedness is defined. A supervoid can arise when several large basins overlap and the tracer density is low enough that the ridges between them are weakly marked. It can also arise when a broad region of space is below average density on very large scales. In such cases, different algorithms may merge the region into one object or split it into several, depending on how they treat shallow ridges. The most stable features are the deepest basins that persist under many reasonable definitions. The most sensitive features are intermediate regions where contrasts are weak and sampling noise can create or erase a boundary. To compare voids across surveys and with theory, analysts often stack them. Many voids are centered, scaled by effective radius, and averaged to produce a mean density profile. This reveals a typical pattern of a low interior and a rising edge, while also showing that the mean void looks more spherical than any single example because asymmetries average out. Individual voids remain irregular, but the stacked profile provides a stable summary for cosmological tests. A further practical measure is the void's central depth, often expressed as how far the interior galaxy density falls below the survey mean after corrections. Deeper voids tend to have cleaner boundaries and are less sensitive to small changes in tracer selection, while shallower voids blend into the ordinary fluctuations of the web. This depth, together with effective radius, helps distinguish a prominent basin from a chance gap in a sparse sample. Redshift space distortions add a final geometric caution. Outflow velocities from void interiors can slightly compress a void along the line of sight in redshift space, while dense regions often appear stretched by internal motions. These effects can be modelled, but they remind that the observed shape depends on both real geometry and velocity fields. In this geometric region, voids are understood as volumes with a measured size scale, an irregular shape, a boundary profile, and a place in a nested hierarchy. Small voids can merge into larger basins, and small underdensities can be erased when embedded in larger overdensities. The largest underdense complexes can be described as supervoids, though their exact segmentation is method-dependent. Observations indicate that void-size distributions and stacked profiles are broadly consistent with the cosmic web seen in simulations. While individual void shapes and merger histories depend on tracer density and on the chosen identification method, it remains uncertain how to define a single universal void boundary across all surveys and tracer populations, because the density field is continuous and different algorithms draw edges in different ways. A cosmic void appears empty because galaxies are scarce, yet the dominant mass component of the universe does not disappear there. Dark matter remains inside voids as a diluted background. In standard cosmology, this follows from how structure begins. The early universe carries small fluctuations, not clean holes. A region that starts slightly underdense expands relative to the mean and loses matter to its surroundings, but it begins with matter, and it retains matter. The word empty therefore describes contrast, not absence. Dark matter behaves differently from ordinary gas. It does not collide and form pressure shocks in the same way that gas does. Streams pass through one another and mix gravitationally without producing a sharp compressed front. This collisionless behavior makes void interiors comparatively smooth. Dense regions sharpen because converging flows pile up. Underdense regions broaden because flows diverge outward. The interior becomes a gentle basin in the mass field, lower than average yet rarely close to zero. The difference between a void in galaxies and a void in mass is amplified by how galaxies form. Galaxies occupy dark matter halos, and halos form where the mass field is high enough to collapse into bound structures. Inside voids, the halo population shifts toward lower masses. Massive halos become rare because the region lacks the deepest gravitational wells. Smaller halos still form because the field is not perfectly uniform and because local fluctuations persist. Many of these halos host no bright galaxies. Gas can be heated, stripped, or prevented from cooling efficiently, leaving dark halos as invisible residents of the void interior. The result is a region that can contain many small halos and a continuous dark matter background while still looking nearly empty in a survey that sees only luminous galaxies. Void mass is measured through gravity rather than through starlight. One method is weak gravitational lensing, the tiny distortion of background galaxy shapes by intervening mass. A single void produces a weak signal, but many voids can be stacked. Their centers are aligned and their sizes scaled so that the average profile emerges. The stacked signal shows a slight tendency for background shapes to be distorted in a way consistent with a central mass deficit and a surrounding ridge where matter is more concentrated. This pattern matches the idea of matter moving out of the interior and collecting toward the boundary. It also provides a way to compare observations to simulations using the same void definitions. Another method uses motions. Galaxies do not follow pure cosmic expansion. They also drift under local gravity, and these peculiar velocities reveal the shape of the mass field. Around voids, the velocity field tends to point outward from the interior toward the denser walls. This flow is gentle compared with the fast random motions inside clusters, yet it is coherent over large scales. When measured statistically, it supports the picture of a gravitational basin with lower density at the center and higher density near the boundary. The same effect appears as a specific form of redshift space distortion, because velocities shift measured redshift slightly and can change the apparent shapes of voids along the line of sight. Dark matter inside voids is not featureless. Simulations show that even large void interiors contain a faint internal skeleton, a miniature version of the cosmic web made of thin filaments and small knots. These features arise from the same initial fluctuations that build the large web, but they grow more weakly because the surrounding density is low. The internal skeleton can host small groups and connect isolated galaxies across the void. Observationally, hints of this structure appear when surveys are deep enough to include faint galaxies and when voids are defined with dense tracer samples. The internal network remains sparse, yet it explains why voids are not perfectly smooth cavities. Void galaxies are a visible sign of this residual structure. They are uncommon compared with galaxies and filaments, but they are expected in any underdense region that still contains halos. Their environments tend to be quieter. Close encounters and mergers are less frequent because neighbors are farther away. Many void galaxies retain gas and continue forming stars, while also remaining smaller on average because the halos that host them are less massive. Their properties vary, and some resemble ordinary small field galaxies, but in large samples their isolation and lower typical halo mass become clear. These galaxies do not weaken the concept of a void. They define it more precisely as a region of reduced abundance rather than a region of absolute absence. A persistent misunderstanding treats emptiness as a binary state, present or not present. Cosmology treats it as a fraction. a region can be missing a large share of its expected galaxies and still contain a substantial fraction of the mean mass density in dark matter. The presence of a few galaxies in such a volume is then normal, because even a low probability repeated across a huge volume produces some outcomes. This is why voids occupy most of the universe's volume without being literal vacuums. They are the wide interiors of a foam-like pattern, filled with a thin background of mass and a small number of structures. Within this region of the topic, the interior of a void is understood as diluted matter rather than empty space. Dark matter provides a smooth background that is lower than average. Small halos and faint internal filaments provide substructure, and a sparse population of galaxies marks the rare places where gas cools and forms stars. Observations indicate that stacked weak lensing and measurements of galaxy flows support a real mass deficit in void interiors with enhanced density near void edges, and that void galaxies exist as a natural outcome of residual halos within underdense regions. It remains uncertain how precisely the relationship between galaxy counts and underlying mass varies across different galaxy types and survey depths, because the mapping from dark matter halos to visible galaxies depends on complex star formation physics and on how surveys select their traces. A void is not carved by an explosion or by removal. It is shaped by gravity acting on a slightly thinner beginning. In the early universe, matter is nearly uniform, yet not perfectly. Tiny variations in density are present across all scales. These variations are measured in the cosmic microwave background and inferred from the distribution of galaxies today. Over time, gravity amplifies the variations. Dense regions pull in more matter and become denser. Underdense regions lose matter and become more underdense. Voids are therefore the natural counterparts of clusters and filaments, formed from the same initial field, but evolving in the opposite direction. The earliest stage is best described as a field of small perturbations. The universe expands, and within that expansion matter has small regions where density is slightly above or slightly below the average. The differences are small, yet gravity is patient. An overdense region slows its local expansion relative to the mean, and can eventually collapse along one or more directions. An underdense region expands more quickly than the mean because it has less gravity pulling inward. This faster local expansion is not a separate expansion law. It is the same cosmic expansion with a smaller gravitational deceleration. As time passes, the overdense parts grow into the visible cosmic web. Matter streams toward them. The web's boundaries sharpen. The underdense parts, meanwhile, become the interiors. Their density drops relative to the mean as matter is drawn outward and outward flows develop. A void, therefore, is not made by pushing matter away with a force. It is made because surrounding structures pull matter toward themselves, leaving less behind. This process is often described in terms of evacuation. Matter in the interior has small random motions and a coherent drift driven by the gravitational potential, shaped by the surrounding density field. The potential is higher in underdense regions and lower in overdense regions in the sense that particles move downhill toward denser structures. The drift is gentle on human scales, but over billions of years it rearranges where mass resides. The interior becomes more uniform because collisionless dark matter streams past through one another, and because small-scale differences are stretched by the faster expansion. The boundary becomes more prominent because matter accumulates in the surrounding ridge and filaments. Void growth can also be described as a sequence of mergers. Small underdense basins exist early, each surrounded by slightly denser ridges. As the universe evolves, the ridges between neighboring basins can thin. The basins effectively merge into larger voids. This is void coalescence, a coarsening process. It does not require that basins become completely empty before merging. It requires only that the separation between them becomes less significant compared with the overall deficit, and that the flow field treats them as one larger region. In simulations, this process is visible as a gradual enlargement of the largest voids and a reduction in the number of small voids as they are absorbed into larger structures. At the same time, voids do not grow without constraint. The density field is not a set of isolated bubbles, it is a continuous landscape. Some underdense regions sit inside larger underdensities and therefore expand freely. Others are embedded within a larger overdensity that is collapsing. In the latter case, the surrounding region's collapse can squeeze the underdense pocket, reducing its volume and erasing it as a distinct void. This is sometimes described as void in cloud evolution. It explains why voids are not found everywhere, and why some small underdensities do not survive to become large cavities. Their environment determines their fate. The role of dark energy enters through growth rate. In the standard cosmological picture, the expansion of the universe accelerates at late times. Accelerated expansion slows the growth of structure because it stretches space and reduces how effectively gravity can gather matter over large distances. For voids, this also changes growth. In a matter-dominated era, both overdense growth and void evacuation proceed efficiently. In an accelerated era, the pace of change slows. Voids still exist and still expand relative to the mean, but their contrast growth becomes less rapid than it would be in a purely matter-dominated universe. This makes voids sensitive to cosmology, because their size distribution and density profiles reflect not only initial conditions but also the later expansion history. Gas adds a second layer. Ordinary gas responds to gravity like dark matter, yet it also has pressure and can be heated. In filaments and clusters, gas can shock and heat as it falls in. In voids, gas tends to remain cooler and less shocked because flows are gentler and densities are lower. This helps gas remain diffuse and ionized. It also means that baryonic physics can change the visibility of void structure, especially in the smallest halos. Heating from ultraviolet background radiation can prevent gas from cooling and forming stars in small halos, making the interior look emptier in galaxies than the dark matter distribution alone would suggest. The internal structure of voids reflects the initial spectrum of fluctuations. No region begins perfectly smooth. A void interior retains small fluctuations that can form small filaments and small halos. These structures grow more slowly because the background density is low, but they do grow. The result is a faint internal network that is most visible in simulations and in deep surveys. This internal network also provides paths for limited mass flow inside voids, channeling matter toward the boundary ridges. The edge of a void is also a dynamic region. Outflow from the interior meets the slower expansion and higher density of the surrounding web. Matter piles up, building the ridge. This ridge can become a site of filament formation and of galaxy group growth. The ridge is not a static shell. It evolves as matter continues to stream and as neighboring voids merge. In some cases, the ridge can become strongly overdense, while in others the contrast remains modest. This variation reflects the larger scale environment and the history of adjacent structures. In this time region, voids are understood as a natural outcome of gravitational amplification of initial fluctuations. They expand relative to the mean, lose matter to surrounding structures, merge into larger basins, and can be erased when embedded in larger collapsing environments. Their evolution is slowed at late times by accelerated expansion, and their visibility in galaxies is shaped by how baryonic physics regulates star formation in low-mass halos. Observations indicate that the general pattern of void growth and void merging appears in simulations that match large-scale structure statistics, and is consistent with the distribution of underdense regions seen in galaxy surveys. It remains uncertain how precisely baryonic feedback and the ultraviolet background alter the detailed density profiles and internal substructure of voids, because these processes can change the galaxy halo connection in the low-density regime and therefore change how voids are traced by light. A void is not only a region of fewer galaxies, it is a region with a characteristic flow. Matter moves through the cosmic web, not as a steady river, but as a slow drift shaped by gravity and expansion. In dense regions, galaxies fall inward toward clusters and move rapidly in random directions inside gravitational wells. In underdense regions, the pattern is quieter and more coherent. The interior tends to empty outward. Galaxies and dark matter drift away from the center and toward the boundaries, following the gradient of the surrounding mass field. These motions are described as peculiar velocities, the component of motion that is not due to the overall expansion of the universe. In an expanding universe, distant galaxies recede on average, and their recession speed increases with distance. Peculiar velocities are the departures from that average, caused by local gravitational attraction and repulsion in the sense of underdensity. A region that is underdense produces a weaker inward pull on its contents, and the surrounding denser regions exert a stronger pull outward. The net effect is an outward flow. The flow is not uniform in all directions because the void boundary is not uniform. Filaments and walls surrounding a void are arranged unevenly, and their gravity pulls more strongly in some directions than others. The resulting velocity field can show preferred pathways toward the nearest walls and toward the nearest nodes. In this way, a void is a basin in density, but also a basin in potential that guides motion towards surrounding ridges. The motion is slow by terrestrial standards, often hundreds of kilometers per second rather than the thousands common in cluster interiors, yet it is steady and coherent over large volumes. Observationally, peculiar velocities are hard to measure because distance measurements are difficult. Redshift includes both cosmic expansion and the line-of-sight component of peculiar velocity. To separate them, an independent distance indicator is needed, such as standard candles or standard rulers, and those are not available for every galaxy. For void studies, velocities are therefore inferred statistically. One approach looks at how voids appear in redshift space, the space defined by angular position and redshift-derived distance. Outflow velocities from a void tend to compress it along the line of sight in redshift space, because galaxies on the near side flow outward toward the observer, reducing their redshift, while galaxies on the far side flow outward away from the observer, increasing their redshift. The result is a slight squashing compared with real space. This effect is subtle and requires many voids to detect robustly, but it becomes a measurable anisotropy in stacked void shapes. Another approach uses the distribution of galaxies around voids. If galaxies are streaming outward, their density as a function of distance and angle shows characteristic patterns. By modeling these patterns within the framework of gravitational growth, observers infer the velocity field parameters that best fit the data. The same modeling can be used to test the growth rate of structure, a quantity that depends on cosmology and on the theory of gravity. Voids, because they are relatively clean environments with less nonlinear clustering than dense regions, can provide a useful complement to cluster-based measurements. Within simulations, the void velocity field is clear. Dark matter particles and halos show outflow from the interior, and the divergence of the velocity field, the measure of how much flow spreads outward, is positive in void interiors. In contrast, It is negative in collapsing regions where matter converges inward. This difference is part of why voids can be treated as dynamical objects rather than only geometric ones. A void is not a static empty space. It is a region with an evolving flow that continues to move matter toward its boundaries. The velocity field also explains why void interiors become smoother with time. Outflow stretches small inhomogeneities and dilutes them. In overdense regions, inflow compresses inhomogeneities and makes them clump. In underdense regions, outflow spreads them. This is another way to understand the relative uniformity of void centers in simulations. It is not that void centers begin uniform. It is that the flow tends to flatten the field there. At the edges, flows are more complex. As matter streams outward from the interior, it meets regions of higher density and sometimes regions of converging flow from neighboring voids. The boundary can become a site of shear, where different flow directions meet. This shear can contribute to the formation and sharpening of filaments. In this way, void outflows and filament growth are linked. The growth of the web is not only matter falling into nodes, it is also matter leaving voids and feeding the same nodes through filaments. Peculiar velocities also affect how voids are used as cosmological probes. Because redshift measurements include these velocities, void shapes in redshift space are distorted. If the growth rate is different, the distortion differs. This provides a test, but it also requires careful modeling of galaxy bias and of how galaxies populate halos in void environments. A tracer population that responds differently to the underlying velocity field can alter the measured anisotropy. For this reason, void velocity studies often rely on comparisons with simulations that include the same tracer selection and use consistent void-finding definitions. The outward drift of galaxies also has practical consequences for void galaxies. A galaxy forming in a void interior can be slowly carried outward over time, and the region's low merger rate means it may evolve in relative isolation. Over time, the galaxy's position relative to the void center can change, and the boundary region can become a place where void galaxies accumulate. This contributes to the appearance of a ridge in galaxy density near void edges, not only because matter is denser there, but also because the flow transports tracers toward that region. In this motion region, a void is described as an expanding basin with coherent outflow. The interior tends to have a divergence that signals expansion relative to the mean. The edges tend to collect matter and show more complex shear and convergence where filaments and walls reside. Observations indicate that statistical measurements of redshift space distortions around stacked voids support the presence of coherent outflows and allow constraints on the growth rate of structure. It remains uncertain how precisely galaxy bias and tracer selection influence these inferred velocity fields, because the mapping from mass flow to galaxy flow depends on how galaxies populate halos and on how surveys sample the void interior and edges. Inside a void, galaxies are sparse, yet most of the ordinary matter is not in galaxies at all. It is in diffuse gas spread between them. This gas is part of the intergalactic medium, a thin mixture of mostly hydrogen and helium that fills the space between galaxies throughout the universe. In voids, this medium is even thinner than average. It is also usually ionized, meaning its electrons are not bound to nuclei, because ultraviolet radiation from galaxies and quasars keeps hydrogen largely stripped in the modern universe. The density of this gas is extremely low. Even outside voids, intergalactic densities can be only a few atoms per cubic meter in many regions. In voids, the density can be lower still, yet the volume is enormous, so the total mass of gas in voids can still be significant when integrated over the whole region. This is one reason the word empty needs careful handling. A void can be missing most of its expected galaxies, and still contain a vast amount of diffuse material that is simply too thin to glow brightly. Gas in low-density regions is heated and cooled through a balance of processes. The main heating source at late times is the ultraviolet background, the cumulative ultraviolet radiation from galaxies and quasars. When ultraviolet photons strike neutral hydrogen, they can ionize it, freeing electrons and depositing energy. The resulting plasma has a temperature that often sits around tens of thousands of degrees Celsius in many intergalactic regions, though exact values depend on density, radiation intensity, and the timing of reionization history. Cooling occurs through expansion and through radiation from recombination and line emission, though at very low densities cooling is slow because collisions are rare. Voids are often cooler than dense regions in a particular sense. In filaments and near clusters, gas falls into gravitational wells and can shock, converting infall speed into heat. This produces the warm-hot intergalactic medium, gas at temperatures of hundreds of thousands to millions of degrees Celsius in some regions. In voids, infall and shock heating are weaker because gravitational gradients are smaller and flows are gentler. The gas can therefore remain closer to the photoionized temperature set by ultraviolet radiation, though pockets of warmer gas can still exist depending on local conditions and past heating. Detecting this gas directly is difficult. At such low densities, emission is faint because emission processes often depend on collisions between particles. Fewer collisions mean less emission. The standard method is absorption. A bright background source, such as a quasar, provides a continuum of light. As that light passes through intergalactic gas, atoms and ions absorb specific wavelengths. The most famous feature is the Lyman alpha line of hydrogen, which produces a pattern of absorption lines known as the Lyman alpha forest. Each absorption line corresponds to gas at a particular redshift along the line of sight. Many of these absorbers are in mildly overdense filaments, but some correspond to lower density gas, including gas in and around voids. In voids, the hydrogen absorption is weaker because density is lower, yet it can still be present. A small column of gas over a long distance can still produce a detectable absorption feature. Observers use many lines of sight and compare absorber properties with galaxy maps. When an absorber lies in a region with few galaxies, it is interpreted as tracing void gas or gas near a void interior. This approach reveals that voids contain ionized hydrogen, and that the intergalactic medium is present even where galaxies are scarce. Metal absorption provides another clue. Metals, in astronomy, are elements heavier than helium. They are produced in stars and spread by winds and outflows from galaxies. In dense regions, metal lines are more common because galaxies are common and enrichment is strong. In voids, metal lines are rarer and weaker because fewer galaxies exist to enrich the gas. Yet metals can still be found in some void regions, implying that outflows can propagate over large distances, or that small galaxies within or near voids contribute modest enrichment. The distribution of metals in void gas is therefore a tracer of how far galactic feedback reaches and how mixing proceeds in low-density environments. The ionization state of void gas is also not fixed. It depends on the ultraviolet background intensity and spectrum, which changes over cosmic time and varies with environment. Near a bright galaxy or quasar, local radiation can increase ionization beyond the background. Far from sources, recombination can make gas more neutral, especially in denser pockets. In voids, densities are low, so recombination is slow and ionization can remain high. This tends to make hydrogen highly ionized, reducing the fraction of neutral hydrogen that produces strong absorption. Even then, the small neutral fraction can still be detected because the path length is long. In addition to ultraviolet ionization, there is a slow heating from cosmic structure growth. As matter moves and small-scale structures form, some kinetic energy is dissipated. In voids, this is weaker than in filaments, but it is not zero. Small halos and faint filaments inside voids can host mild shocks and warm gas. This contributes to a diversity of temperatures rather than a single value. Simulations predict that void gas is typically cooler and less shocked, while dense regions host a larger fraction of warm-hot gas. Voids also influence how gas accretes onto galaxies. In dense regions, filaments supply a steady flow of gas into halos. In voids, supply is thinner and more isotropic, and the rate at which halos gain new gas can be lower. This affects star formation in void galaxies, not necessarily by shutting it off, but by changing its pace and its bursts. The low interaction rate can allow gas reservoirs to remain undisturbed, while the low external pressure can make outflows escape more easily, depending on halo mass and feedback strength. The intergalactic medium within voids therefore acts as both content and context. It is content because it contains ordinary matter that participates in the cosmic baryon budget. It is context because its thinness and temperature shape the evolution of the few galaxies that live there and the way radiation propagates through space. Observations indicate that absorption studies reveal ionized hydrogen throughout the intergalactic medium, including in low-density regions associated with voids, and that metal enrichment is weaker but not always absent in these environments. It remains uncertain how uniformly metals are mixed into void gas, and how far feedback-driven enrichment travels over cosmic time, because this depends on the history of outflows, the geometry of the web, and the efficiency of mixing in very low-density plasma. Light passes through voids the way wind passes through a valley, shaped subtly by what is missing and by what remains. A cosmic void is a mass deficit, and a mass deficit is also a feature in the gravitational landscape of the universe. Photons do not notice whether the matter is luminous or dark. They respond to gravity through the curvature of space-time. As a result, voids leave gentle imprints on the appearance of background galaxies and on the oldest light of all, the cosmic microwave background. The first imprint is lensing. Gravitational lensing is the bending of light by mass. A dense cluster acts like a converging lens, focusing light and magnifying background galaxies. A void tends to act in the opposite sense. Because it contains less mass than average along a line of sight, it produces a slight defocusing. Background galaxy images are distorted in a coherent way that, when averaged over many sources, implies a central deficit of projected mass. The effect is small because voids are not empty and because the mass contrast is modest, but it is measurable statistically. In practice, a single void is rarely strong enough in lensing to stand out above noise. Galaxy shapes have intrinsic variety, and measuring a tiny systematic distortion requires averaging many galaxies. Analysts therefore stack voids. Many voids are centered and scaled by their effective radius. Then background galaxy shapes are averaged in a newly. The resulting mean pattern shows a slight negative convergence in the center, meaning a projected mass deficit, and often a surrounding positive ridge where matter is enhanced near void edges. This matches the physical picture of evacuated interiors and denser boundaries. The lensing signal depends on how voids are defined, because different void finders select different parts of the density field. Deep, large voids tend to produce a clearer stacked signal. Shallow voids produce a weaker signal that can blend with ordinary fluctuations. The signal also depends on the redshift distribution of background galaxies, because lensing efficiency depends on geometry. A void at a given distance lenses galaxies behind it, and the strength depends on the relative distances between observer, void, and source. Modern surveys measure photometric redshifts for background galaxies and use them to weight the lensing analysis, reducing contamination by galaxies that lie in front of or inside the void. Void lensing also has a related imprint on the cosmic microwave background through lensing of the background itself. The microwave background is a map of small temperature fluctuations from the early universe. As its photons travel through the cosmic web, their paths are deflected. This weak lensing remaps the pattern, smoothing some features and coupling large and small scales. Voids contribute to this remapping as part of the total mass distribution. Their individual contribution is small, but in principle stacking void positions on a microwave lensing convergence map can reveal a mild mass deficit consistent with the void interior. This is a way to connect galaxy-defined voids to mass traced by the microwave background lensing field. A second imprint is an energy shift rather than a path deflection. As a photon crosses a gravitational potential, it gains energy falling in and loses energy climbing out. If the potential does not change during the crossing, the gain and loss cancel, leaving no net effect. When the potential evolves while the photon is inside, the cancellation fails slightly. The net effect is a small change in photon energy that appears as a tiny temperature shift in the cosmic microwave background. This is called the integrated Sachs-Wolf effect, an accumulated gravitational redshift effect along the line of sight. In the standard cosmological picture, the relevance of this effect depends on cosmic time. In an era when matter dominates and structure grows efficiently, large-scale gravitational potentials remain nearly constant in linear theory, so the net effect is small. At later times, when accelerated expansion becomes important, the growth of structure slows, and large-scale potentials tend to decay in amplitude. A photon crossing such a decaying potential experiences an imbalance. For a void, the sign tends to produce a slight cooling, meaning the microwave background appears slightly colder in that direction. For a supercluster, the sign tends to produce a slight warming. This imprint is weak. Typical temperature shifts expected from individual voids are much smaller than the primary fluctuations imprinted at the last scattering surface. For this reason, the effect is usually sought through statistical correlation rather than through individual features. One approach cross-correlates microwave background maps with large-scale structure maps, showing that, on average, regions with more matter tend to align with small warm shifts, and regions with less matter tend to align with small cool shifts. Another approach stacks microwave temperatures at the locations of many voids and measures the mean temperature profile. Some analyses report a small mean cold imprint associated with void centers and, in some cases, a weak surrounding warm tendency linked to compensation at the edges. The amplitude and significance depend on void selection, redshift range, and filtering scale, and results vary across studies. A related secondary effect is nonlinear evolution. As structures grow and change shape, potentials can evolve in more complex ways than in the linear picture. This can produce an additional small imprint often grouped under the name Rees-Siyama effect. In void contexts, it represents the contribution from the detailed nonlinear evolution of the void and its ridge. For the largest voids, the linear integrated effect is often treated as the dominant expectation in standard models, while nonlinear corrections remain smaller. The precise balance remains uncertain because it depends on void profiles, compensation, and the accuracy of modeling in the mildly nonlinear regime. The lensing and integrated effects are connected by the same underlying mass field, yet they are not identical probes. Lensing depends on the projected mass distribution along the line of sight, and does not require the potential to evolve. The integrated temperature effect depends on time evolution of the potential during the photon crossing, and therefore depends on cosmology. This difference makes voids useful as cosmological laboratories. A void that is clearly seen in galaxy surveys and that has a measured lensing mass deficit provides a geometric and gravitational anchor. The microwave temperature imprint expected from it then tests how potentials evolve, and therefore tests the expansion history and the growth of structure. There is also a practical limit. The microwave background contains intrinsic fluctuations of its own, and those fluctuations are larger than the expected void imprint for a single object. Even stacking many voids can leave results sensitive to choices of filter and void definition. In addition, the galaxy catalogue used to define voids is itself a tracer sample with bias, and different galaxy selections can yield different void populations. These layers of dependence do not erase the physics. They define why void imprints are measured as averages and correlations rather than as sharp signatures in single objects. In this photon region, voids are understood as gentle gravitational basins. They defocus background galaxy shapes through weak lensing, producing a measurable projected mass deficit when many voids are stacked. They can also shift microwave photon energies slightly through evolving potentials, producing a small average cold imprint that is most relevant at late cosmic times. Observations indicate that stacked void lensing is consistent with underdense mass profiles, and that cross-correlations between the microwave background and large-scale structure detect a late-time integrated effect in an average sense. It remains uncertain how large the mean microwave imprint of voids should be for specific void selections, because the expected amplitude depends on void profiles, compensation, tracer definitions, and the details of potential evolution in the late universe. In cosmology, voids are useful because they are simple in one important way. They are regions where density is low, where gravitational clustering is weaker, and where the complicated physics of crowded environments plays a smaller role. Clusters contain hot gas, mergers, and strongly nonlinear motions that are difficult to model in detail. Voids are quieter. Their interiors evolve more gently, and their average profiles can often be described with fewer assumptions. This relative simplicity turns absence into measurement. One of the most direct uses of voids is statistical counting. A survey can identify many voids and measure how many appear at each size and depth. This distribution, the void size function, depends on how structure grows. Faster growth evacuates underdense regions more efficiently and changes the balance between small basins and large cavities at a given cosmic time. Slower growth produces a different balance. Because growth depends on the expansion history, void counts carry information about dark energy through its influence on late-time structure formation. The same distribution is also sensitive to the overall matter content and the amplitude of early fluctuations. So void counts are most valuable when combined with other probes that constrain these parameters in different ways. A second use relies on geometry. The universe is statistically isotropic on large scales, so a void, when averaged over many examples, is expected to be round in real space. In observed maps, converting redshift to distance requires an assumed cosmology, if that assumption is slightly wrong. The scaling along the line of sight differs from the scaling across the sky, and a round object can appear stretched or squashed. This is the Alcock-Paczynski idea applied to voids. By measuring the average shape of stacked voids and accounting for known velocity distortions, analysts infer the distance redshift relation that best restores isotropy. This provides constraints on expansion that complement supernova distances and baryon acoustic oscillation measurements. Peculiar velocities do not disappear in this approach, they become part of the signal. Voids have coherent outflows that produce characteristic redshift space distortions, and those distortions depend on the growth rate of structure. When the void galaxy correlation is measured in redshift space, it shows anisotropy that reflects both geometry and dynamics. A model that includes the expected outflow pattern can fit this anisotropy and extract parameters that describe growth and expansion together. This is attractive because it uses the same galaxy dataset to probe both the background expansion and the response of matter to gravity. When lensing measurements are added, the mass deficit of the same void sample is checked directly, helping separate tracer effects from true changes in the density field. Voids also provide a complementary view of the baryon acoustic oscillation feature. The characteristic separation scale imprinted in the early universe is usually measured from galaxy pairs, yet it can also be recovered using void centers or galaxy distributions around voids. The weighting is different because void environments emphasize low-density regions, so the result acts as an internal cross-check rather than a replacement. When it is consistent, it supports the overall geometric calibration of the survey volume. In some analyses, void-based statistics reduce sensitivity to certain nonlinear clustering effects that complicate dense regions. Because void interiors are less affected by strong small-scale merging. Another sensitivity arises in theories that modify gravity. Many such models are constructed to look like general relativity in dense environments, while allowing larger deviations where density is low. This is often described as screening. Voids, being low density, can be places where screening is weaker and deviations are more visible. In those models, void expansion, void lensing profiles, and outflow patterns can shift. Measuring void lensing and void dynamics therefore tests whether gravity behaves the same in low-density regions as it does in high-density regions. While remaining careful about tracer bias and survey systematics, the same data can also be compared across redshift. Because a time-dependent deviation would change void evolution differently at different cosmic epochs. Voids are also mildly sensitive to light. Fast particles such as neutrinos. Neutrinos carry mass but do not cluster strongly on small scales, and their motion smooth structure. In models with more neutrino mass, the contrast of the cosmic web is reduced, and void interiors can be slightly less depleted in the matter field. This effect is subtle, yet it contributes to joint constraints when combined with other clustering measures that respond differently to neutrino smoothing, such as the abundance of massive clusters and the overall shape of the matter power spectrum. For all these applications, calibration against simulations is essential. A simulation begins with initial fluctuations consistent with early universe constraints and evolves dark matter and, in more detailed runs, gas and star formation. Synthetic galaxy catalogues are built to match the observed tracer population, including selection effects and redshift uncertainties. This same void-finding algorithm is applied to the mock catalogue, producing predictions for void counts, stacked shapes, lensing profiles, and redshift space distortions under a given cosmology and gravity model. Observations are then compared to these predictions in a like-for-like way. This also allows uncertainty estimates to include the look-elsewhere character of searching for voids across many scales. Uncertainty remains because voids are defined by the tracers used to find them. A survey that selects red, massive galaxies produces a different void catalogue than one that selects fainter or more star-forming galaxies. Photometric redshift errors smear structures and can merge or split voids. Mask edges can create false underdensities if not modelled carefully. These effects are managed through consistency checks and through mocks that include the same observational limitations, but they set a floor on precision and they motivate using several tracer definitions to test stability. In the calm accounting of modern cosmology, voids become tools because they respond to gravity and expansion in measurable statistical ways. Their abundance reflects growth. Their stacked shapes and redshift space anisotropies probe geometry and dynamics together. Their lensing profiles test the mass deficit directly and can help test gravity in low-density regimes. Observations indicate that void-based measurements become increasingly informative as surveys map larger volumes with higher tracer density. It remains uncertain how far void constraints can be pushed before they become limited primarily by tracer bias and void definition dependence, rather than by raw statistical power. One particular void story becomes widely discussed because it connects a low-density region to a famous feature in the cosmic microwave background. The feature is the cold spot, a broad patch of slightly lower temperature than the surrounding microwave sky. The temperature difference is small in absolute terms, yet the patch is large on the sky and appears unusual under some ways of filtering and measuring. Because voids can leave a faint, cool imprint on the microwave background through evolving gravitational potentials, the cold spot is sometimes framed as a question of whether a very large underdensity sits along that line of sight. The cold spot is first a map feature. The cosmic microwave background is the afterglow of the early universe, released when the plasma becomes transparent and photons begin to travel freely. Its temperature field contains tiny fluctuations produced by early density and velocity patterns. Those fluctuations form a mottled sky with structure on many angular scales. In such a field, broad cold and warm regions naturally exist. A cold spot is therefore not a different kind of phenomenon from other patches. It is a particular region that becomes prominent under specific statistical descriptions. The line of reasoning that links a void to the cold spot begins with gravity. Photons crossing the universe fall into and climb out of gravitational potentials. If a potential remains constant during the crossing, energy gained is balanced by energy lost. Leaving no net change, when the potential evolves, the balance is imperfect. In the late universe, accelerated expansion slows the growth of structure and makes large-scale potentials decay in a way that allows a small net energy shift. An underdense region can then leave a slight cooling imprint in the microwave background, an integrated Sachs-Wolf contribution. This contribution is real in the standard picture, yet it is usually small compared with the primary temperature fluctuations created at the last scattering surface. For that reason, the cold spot story is not about whether voids can produce any imprint. It is about whether a void of plausible size and depth can produce enough imprint to account for most of the observed dip, and whether the observed galaxy distribution supports such a void. The proposed structure is often described as a supervoid in the general direction of the cold spot. The claim is not that space there is empty, but that galaxy surveys show fewer galaxies over a broad region of distance than average. Some analyses report a deficit in tracer counts that extends across a substantial fraction of a billion light-years in co-moving scale, with a central region of lower density and a gradual return toward average at larger radius. The inferred structure can look like one extended basin or like several underdense regions that overlap in projection. Interpreting these findings requires care because galaxy catalogues do not trace matter uniformly. Bright galaxies avoid low-density regions more strongly than mass does, and photometric redshift uncertainty can smear depth, blending smaller basins into one broader feature. Survey completeness and dust corrections also matter because small gradients can mimic a deficit. For these reasons, the line of sight is often treated as evidence for some underdensity, while its exact size and depth remain method-dependent. Weak gravitational lensing provides an independent check because it traces mass more directly. Analyses of wide imaging data can indicate a projected mass deficit aligned with the cold spot direction, consistent with an underdense corridor. The lensing signal is modest and noisy, as expected for such large scales. Yet it supports the idea that the line of sight is not typical in the matter field. This check does not demonstrate that the void is extreme enough to create the cold spot. It mainly confirms that the deficit is not purely a tracer artifact. The next step is sufficiency. Models that compute the expected integrated Sachs-Wolf imprint from a large void use its estimated profile and redshift. In the simplest treatments, the predicted temperature shift tends to be smaller than the full cold spot dip as commonly described in filtered maps. The expected imprint is also smooth and broad, and if the void is partly compensated by a denser ridge near its boundary, the average temperature profile can include a weak surrounding warm tendency. Such shapes can resemble aspects of the cold spot's filtered appearance, yet the amplitude often remains limited. A conservative mixed picture follows naturally. The cold spot can be primarily a primordial fluctuation that happens to be a deep minimum in the random field, with the underdensity adding a smaller extra cooling that makes the total more notable. This mixed picture remains compatible with the general expectation that single void imprints are weak, and that most of the microwave pattern is set at last scattering. Statistics adds a further boundary. The cold spot's apparent rarity depends on how it is defined, on filter scale, and on how the search across the sky is counted. When the same procedures are applied to many simulated microwave skies, the feature often remains somewhat unusual but not so singular that it forces a new mechanism by itself. This statistical sensitivity weakens any claim that one structure must be responsible. Polarization adds another constraint. A temperature feature produced at last scattering has a linked polarization pattern, while a late-time integrated imprint adds little polarization on its own. Measurements at these scales are difficult, yet comparisons of temperature and polarization behavior in the cold spot region tend to be consistent with a primarily primordial origin, leaving room for a smaller secondary imprint. This does not exclude a void contribution. It bounds its role. In this region of the topic, the cold spot becomes a case study in how voids relate to other cosmological signals. Observations indicate that a void-like underdensity exists along the cold spot direction at some level in galaxy surveys, and that mass mapping can support a modest deficit. It remains uncertain whether this structure is a single exceptionally large void or a projection of multiple basins, and it remains uncertain how much of the cold spot's temperature depression is attributable to a late-time void imprint versus a rare but allowed primordial fluctuation in the microwave background field. Life inside a void is shaped by quiet conditions. The environment is not empty, but it is thin in both galaxies and gas compared with the crowded boundaries of the cosmic web. A void galaxy often lives far from massive neighbours, far from strong tidal fields, and far from the hot intra-cluster plasma that fills rich clusters. This isolation changes how galaxies grow, how they keep or lose gas, and how often they are disturbed. The most immediate difference is the rate of encounters. In groups and filaments, galaxies pass near one another often enough that gravity can stir disks, compress gas, and trigger bursts of star formation. Major mergers can reshape galaxies, building spheroids and feeding central black holes. In deep void interiors, typical separations are larger and close passages are rarer, simply because there are fewer potential partners. Growth by repeated mergers is reduced, and many void galaxies evolve mainly through internal processes and slow accretion rather than frequent collisions. Gas accretion still continues, but the supply network is thinner. Filaments that feed dense regions are weaker in void interiors, and the surrounding intergalactic medium is more tenuous. A halo in a void can still draw in gas, yet the inflow is often less directed and can be slower on average. The gas that arrives is also less likely to be strongly shock-heated than gas falling into massive filaments and clusters, so it can remain comparatively cool and able to form stars once it settles. At the same time, low density makes gas easier to lose. Star formation produces radiation, winds, and supernova explosions that push on surrounding gas. In dense environments, higher external pressure and a deeper web of surrounding material can help confine outflows and allow some expelled gas to cool and return. In a void interior, external pressure is lower. Outflows can expand more freely, and a larger fraction of gas and metals can escape from low-mass halos. This can slow long-term growth in the smallest systems and can keep void gas more weakly enriched. The halo population inside voids is shifted toward lower masses. Massive halos are rarer, so very massive galaxies are rarer as well. This changes the typical mix of galaxy types. Disk galaxies and small irregular systems become more common relative to dense environments, while the most massive ellipticals, which often form through repeated mergers and dense growth histories, are less frequent in the deepest void centers. Variety remains because void boundaries can host groups, and because the internal web can still create local knots. But the average trend reflects the underlying halo statistics. Morphology follows this statistical difference. With fewer major mergers, disks can survive longer and maintain ordered rotation. Internal instabilities still build bars and spiral structure, and minor encounters still occur. Yet the most disruptive reshaping events are less common. In this sense, void galaxies offer a view of galaxy evolution, where violent external disturbances are reduced. So internal dynamics and slow accretion play a larger role in setting structure. Star formation in voids is not simply lower, it is often steadier, and it can persist because one important quenching channel is weak. Ram pressure stripping, the removal of a galaxy's gas by motion through dense hot medium, is strong in clusters and can be important in some groups. Deep void interiors lack a dense hot background, so this stripping is minimal. Many void galaxies therefore retain gas reservoirs and continue forming stars at rates typical for their mass. The limiting factor is not stripping but supply and feedback. If inflow is slow and outflows escape, a small galaxy can gradually exhaust its cold gas and fade. If gravity retains gas and some expelled material returns, star formation can continue over long spans with intermittent bursts. Chemical enrichment reflects the same balance. Metals are produced in stars and carried outward by winds and supernova ejecta. In voids, galaxies are smaller on average, and some enriched gas can escape more easily into low-pressure surroundings. Accretion from the intergalactic medium can also be relatively metal-poor, diluting a galaxy's gas while sustaining new star formation. The result is that some void galaxies show lower metallicity at a given stellar mass, though the effect is not uniform and depends on each system's history and on how the void sample is selected. Central black hole growth and active galactic nuclei also follow the environment indirectly. The strongest fueling episodes often involve gas driven inward by major mergers or strong interactions. In void interiors, those triggers are less common, and the most massive hosts are rarer. Bright, sustained activity is therefore less common deep inside voids, though low-level accretion can still occur, and some void galaxies can host active nuclei on smaller scales. The surrounding intergalactic medium remains part of the story. Void gas is thin and usually ionized, with long cooling times. When a void galaxy expels gas, that material can travel farther before mixing or falling back, producing patchy enrichment that is difficult to map directly. Absorption measurements along background sightlines show ionized hydrogen throughout low-density space and occasionally weak metal signatures, consistent with modest enrichment even where galaxies are sparse. Void environments therefore provide a clearer stage for separating external and internal quenching. In dense regions, many galaxies stop forming stars because gas is stripped, heated, or prevented from cooling. In voids, those external channels are weaker, so quiescence more often reflects internal balance between inflow, star formation, and feedback-driven loss. Even so, environment still matters because long-term inflow is shaped by the large-scale density field. A void galaxy's quiet life is not isolation from gravity. It is gravity operating with fewer neighbors and a thinner supply network. Life inside a void is ordinary galaxy physics under low-density conditions. Encounters are rarer, external pressures are lower, and the background medium is thinner. The typical result is a population that is smaller, more isolated, more disk-dominated, and more likely to retain gas than galaxies in rich clusters, while still showing diversity set by mass and history. Observations indicate that void galaxies have reduced merger rates and weaker environmental stripping compared with dense environments, and that many remain star-forming for long periods. It remains uncertain how strongly void residence alters long-term metal recycling and gas return, because those processes depend on diffuse flows between galaxies and the surrounding intergalactic medium that are difficult to measure directly in the lowest density regions. Cosmic voids are easiest to understand as a class, yet it helps to anchor them with nearby examples. Close to the Milky Way, the local universe already contains underdense regions that shape the motions of nearby galaxies. These nearby voids are not as vast as the largest cavities mapped across billions of light-years, but they are close enough that their influence appears in local flows and in the distribution of familiar galaxy groups. The local void is one of the best known nearby underdensities. It is described as a region adjacent to the local group, the small collection of galaxies that includes the Milky Way and Andromeda. The local void is not a neatly bounded empty bubble. It is a direction of space where fewer galaxies are found than average compared with other directions at similar distances. It is bounded by local sheets and filaments that host known groups. Its presence is inferred by galaxy maps in the nearby universe and by the way galaxies move, because local peculiar velocities reflect the combined gravitational pull of overdense regions and the relative absence of pull from underdense regions. In the nearby universe, distance measurements can be more direct than in deep surveys. Methods such as standard candles allow redshift-independent distance estimates for some galaxies, helping disentangle local peculiar velocities from the general expansion. This matters because the local universe is not in perfect Hubble flow. Nearby galaxies can have peculiar velocities of hundreds of kilometers per second, comparable to or larger than their recession speed at small distances. A void nearby therefore shows itself both as a gap in the galaxy distribution and as a component in the local velocity field that pushes galaxies outward from its interior. Other nearby underdense regions appear in the larger pattern known as the local supercluster, or Virgo supercluster region, where the Virgo cluster provides a dense node and surrounding filaments and walls shape the distribution. In maps of nearby galaxies, there are broad regions of lower density that sit between the main filamentary structures. Some are associated with named structures such as the Booter's Void, which is often cited as a large void discovered in galaxy surveys. The Booter's Void is not a complete emptiness, but it is notable for its size and for the low number density of galaxies within it compared with surrounding regions. It is an example of how a void can be recognized as a large cavity, even with relatively early survey data, because its galaxy deficit is strong enough to appear even when traces are sparse. When a void is discussed as famous, the name often refers to the sky direction and the survey context rather than to a physically separate entity. Voids are not isolated objects drifting in space. They are regions defined by the surrounding web. Their boundaries are shaped by the placement of nearby filaments and clusters. In the local universe, those boundaries can be associated with recognizable structures, such as the Virgo cluster, the Great Attractor region, and various local sheets of galaxies. A void's identity is therefore tied to the geometry of the nearby web. These local voids also illustrate scale dependence. A region that appears underdense on one scale can contain smaller structures on another. The local void, for example, still contains some galaxies, and some of them can be isolated systems or small groups. The Bhuta's void contains galaxies as well, though fewer than expected for its volume. These interior galaxies can sit on faint internal filaments that are hard to see until the survey is deep enough and the sample is dense enough. This internal structure reinforces that a void is a low-density environment, not a total absence. The local environment also shows that voids influence the shape of surrounding structures. The edges of underdense regions can coincide with walls and filaments that appear more prominent because matter has flowed toward them. The local sheets of galaxies that border the local void can be viewed as part of this process, though in practice many influences overlap because the local universe contains multiple nearby overdensities and underdensities whose gravitational pulls combine. A nearby void is also useful as a training ground for void-finding methods. Because distances can be measured more directly for some local galaxies, and because surveys can detect fainter galaxies nearby, local void catalogues can be cross-checked in more ways than distant ones. Yet local voids also face a limitation. The volume is small compared with deep surveys, so cosmic variance is large. The local pattern is one realization of the cosmic web, and it can be unusual in some respects without implying a global difference. The step from local named voids to the general void population is therefore a step from anecdote to statistics. Named voids help the mind hold a picture. They show that large underdense regions are real, and that they shape galaxy distribution and motion even near the Milky Way. Yet the general properties of voids are established by catalogues with many hundreds or thousands of voids across wide volumes, where averages and distributions can be measured and compared with simulations. In this region, examples serve as anchors. The local void illustrates a nearby underdensity that helps shape local flows. The Bhuta's void illustrates a large cavity recognized in survey maps as a region of unusually low galaxy density. Other named underdensities illustrate that the web is a foam-like pattern with many cavities, not a uniform scatter. Observations indicate that nearby voids are consistent with the same underdensity concept used in deep surveys, and that they contain some galaxies and substructure, while remaining strongly underdense relative to surrounding filaments. It remains uncertain how precisely boundaries and depths of named voids should be defined in a universal way, because local distance measurements, survey completeness, and the continuous nature of the density field make void edges depend on method and tracer choice, even when the region itself is clearly underdense. Simulations provide a controlled universe where voids can be followed from a nearly uniform beginning to the web seen in surveys. The rules are specified. Initial fluctuations are drawn to match early universe constraints, and gravity evolves matter forward in time. When the simulated volume is large enough, the result is a foam-like pattern of filaments and clusters surrounding wide underdense basins. The same void language used for the real sky can then be applied to the synthetic sky, allowing comparisons that would otherwise be difficult. The simplest simulations track only dark matter. Dark matter is represented by many particles that stand in for a continuous mass field. Each particle follows gravity, and the collective motion builds the cosmic web. Voids in these simulations are clear. Their interiors become underdense, their edges develop ridges, and their internal substructure remains faint. The distribution of void sizes and the typical density profile can be measured directly from the mass field without needing galaxies as tracers. Observations do not provide a complete mass map. They provide galaxies, redshifts, and lensing signals with noise. To compare fairly, simulations are turned into mock surveys. A halo finder identifies bound dark matter halos, and a galaxy model assigns galaxies to halos. Some models are statistical recipes chosen to match observed abundances and clustering. Others are semi-analytic prescriptions that track gas cooling, star formation, and feedback in simplified form. The aim is a tracer population with similar selection and clustering to the survey sample used for void finding. More comprehensive simulations include ordinary gas as well. These hydrodynamic simulations evolve gas alongside dark matter, allowing cooling, star formation, and heating by feedback. They can produce more realistic galaxy populations, but they also introduce new uncertainty because star formation and feedback occur on scales smaller than the simulation resolves. Calibrated subgrid models describe how energy from supernovae and black holes couples to gas. In voids, these choices mainly affect the smallest halos, determining whether faint galaxies appear and how enriched the diffuse gas becomes. Void finding is then repeated in the same way as for the real data. The algorithm sees only tracer galaxies and their positions in redshift space. In simulations, true positions and velocities are known, so redshift space distortions can be applied exactly. This allows tests of how much inferred void shapes depend on peculiar velocities and how well models recover the underlying real space structure. Survey limitations are also imposed. A mock catalogue can include the same sky mask, depth variations, and redshift errors as the real survey. The result is a synthetic dataset that fails in the same ways as the data, which prevents misleading comparisons between ideal simulations and imperfect observations. Several checks then become standard. Void abundance is compared by size and depth. Stacked profiles are compared in tracer density and in true mass density. Lensing signals are predicted by stacking the simulated mass deficit and converting it into an expected weak shear pattern. Redshift space anisotropies around voids are modelled to constrain the growth rate of structure. In general, the broad picture matches well. Simulations reproduce a web with cavities that occupy most of the volume, and void statistics are broadly consistent with a universe dominated by dark matter and late-time accelerated expansion. Tensions appear at the level of detail. One source is tracer bias. A void defined by bright red galaxies is not the same physical region as a void defined by faint blue galaxies, and the mapping from halos to visible galaxies is most uncertain in low-density environments. In void interiors, small changes in star formation thresholds can decide whether a halo hosts a detectable galaxy, shifting boundaries and measured depths. Another source is resolution and sampling. If a simulation is too coarse, small internal filaments and halos are underrepresented, making voids appear smoother than they should. If a survey is sparse, it can have the same effect by missing faint galaxies. Baryonic physics adds further uncertainty for gas predictions. Feedback can push gas outward and heat it, changing how baryons trace dark matter. In voids, this affects temperature, ionization, and metallicity in diffuse gas that is usually observed through absorption. Those observations sample limited lines of sight and depend on the assumed ultraviolet background, so the comparison remains partly model-dependent. Real surveys also carry systematics that can mimic or distort voids. Photometric redshift errors smear structure along the line of sight and can merge nearby basins into larger voids. Incomplete sampling and masks can remove galaxies unevenly, altering contrast between boundaries and interiors. MOCs help quantify these effects, but only if the survey pipeline is reproduced accurately. Another layer of comparison comes from trying more than one void definition on the same simulated and observed catalogues. Some algorithms favour the deepest basins, others merge basins into larger complexes, and some define edges by local density ridges. In simulations, the underlying mass field is known, so each definition can be evaluated by asking how well the selected voids correspond to true mass deficits and coherent outflows. In observations, the same exercise reveals how sensitive conclusions are to algorithm choice, smoothing scale, and tracer population. When a result persists across definitions, such as the presence of a central mass deficit and an edge ridge in stacked lensing, it is treated as robust. When a result appears only for one narrow choice, it is treated as provisional and often attributed to selection or filtering. Voids are also used in simulation suites that vary cosmological parameters. Changing the matter density, the fluctuation amplitude, or the late time acceleration changes void statistics in predictable directions, and modified gravity models can change void outflow patterns and lensing profiles most strongly in low-density environments. These predicted differences are then confronted with data, usually through likelihood analysis built on MOC catalogues. The method is conservative because uncertainty from tracer bias and survey systematics are carried forward, so disagreements must be persistent and coherent across multiple measurements before they are taken as evidence against the standard framework. Despite these caveats, simulations are the main reason voids can be treated as precision objects. They provide the mapping from an underdense tracer region to an expected mass deficit and flow field, and they show how voids merge and how ridges form. Observations then test these predictions with galaxy counts, lensing, and microwave background correlations. Where they agree, confidence grows that the large-scale model is sound. Where they differ, the difference points either to survey limitations, to incomplete galaxy modelling in low-density environments, or to a need to refine the cosmological assumptions. Future surveys sharpen void science by doing two simple things well. They map larger volumes and they map them more uniformly. A void is a large object defined statistically, so it benefits from more space to count and from more galaxies to trace its shape. When coverage is wider and tracer density is higher, void catalogues become more complete. Boundaries become less sensitive to sampling noise, and comparisons between different void definitions become more stable. Wider volume reduces cosmic variance. The local universe is one realization of the cosmic web, and small survey volumes can overrepresent or underrepresent rare features such as very large void complexes. When future surveys map many billions of light-years in comoving volume, the distribution of void sizes and depths can be measured with smaller uncertainty. The largest voids become easier to characterize because more of them appear in the sample, allowing the tail of the distribution to be measured directly rather than inferred from a few examples. Higher tracer density changes the interior picture. With more galaxies per unit volume, smaller internal filaments and small halo groups become visible. So voids can be described with richer internal structure rather than as simple empty spheres. This makes void profiles more realistic and allows substructure to be studied. It also allows different tracer populations to be used side by side. One sample can emphasize massive galaxies that trace dense boundaries. Another can include fainter galaxies that populate intermediate densities and partially fill interiors. Comparing voids across these samples helps separate true mass structure from tracer bias. Uniformity matters because void finding is sensitive to spatial variations in survey completeness. If some regions are observed more deeply than others, galaxy number density changes for observational reasons, and this can be mistaken for a void. Future surveys reduce this risk by controlling calibration, by correcting dust extinction more precisely, and by mapping selection functions carefully. In addition, they often provide both imaging and spectroscopy so that redshift uncertainties are reduced. Better redshifts mean less smearing along the line of sight, which reduces false merging of separate basins and improves the fidelity of void shapes. Weak lensing surveys add a direct mass measurement. As imaging quality improves and galaxy shape measurements become more accurate over wider areas, void lensing can be detected with higher significance and on finer scales. This allows mass deficits to be mapped more directly, and allows comparisons between void density in tracers and void density in mass. With enough signal to noise, void profiles can be measured as a function of redshift. Testing whether void growth matches standard expectations and whether any time-dependent deviations appear, CMB lensing maps also improve. As microwave surveys refine polarization measurements and reduce foreground contamination, lensing reconstruction noise falls. This makes it easier to see a subtle deficit associated with voids when many voids are stacked. It also improves the separation between lensing effects and integrated temperature effects. With cleaner maps, the average microwave imprint of voids can be measured more consistently and compared to the mass profiles inferred from lensing and surveys, tightening the link between structure and potential evolution. Spectroscopic mapping adds velocity information. Better redshift precision and larger samples allow redshift space distortion signals around voids to be measured more accurately, constraining the growth rate of structure and testing gravity in low-density regimes. When combined with lensing, which measures mass, the combination can test whether the relationship between potential and density is consistent with general relativity and standard dark energy in a way that is less sensitive to tracer bias alone. Void studies also benefit from improved modeling. Simulations continue to increase in volume and resolution, and include better treatments of baryonic physics and survey systematics. Forward modeling becomes more common, where simulated galaxies are passed through synthetic observation pipelines that mimic the real survey. Then voids are found in the simulated observables. This reduces mismatch between theoretical voids and observed voids, and makes likelihood analyses more reliable. The end result is not that voids replace other cosmological probes, it is that they add an independent channel that is sensitive in complementary ways. Clusters probe the high-density tail of the web, voids probe the low-density tail. If both tails are consistent with the same cosmological parameters, confidence grows. If they differ, the difference provides targeted clues about where models or measurements need refinement. In this final region, voids remain what they are: the largest low-density basins in the cosmic web. Not empty space, but a diluted medium shaped by long gravitational flows. Future surveys reduce the uncertainty in their catalogues, clarify their mass profiles through lensing, and refine their dynamical signatures through redshift space distortions. Observations indicate that void-based methods already detect coherent outflow patterns and lensing mass deficits in stacked samples. and broader surveys can convert these detections into sharper constraints on growth and expansion. It remains uncertain how much void cosmology will ultimately be limited by observational systematics and tracer bias, rather than by statistical power. Yet the direction is steady larger volumes, better redshifts, cleaner lensing maps, and more consistent definitions will make the universe's emptiest regions among its most informative. The cosmic web holds its shape without noise. Filaments and clusters remain bright because matter keeps gathering there, and voids remain wide because matter keeps leaving. The emptiest regions are not holes in space. They are basins in density and in gravitational potential, filled with a thin background of dark matter and ionized gas, and marked by only a few isolated galaxies. Their boundaries are broad ridges where matter accumulates, and their interiors evolve gently, expanding relative to the cosmic mean, and smoothing as outflow stretches what remains. A void is therefore defined by contrast. It is underdense compared with average, not empty in an absolute sense. It is found through careful mapping of galaxy positions in 3 dimensions, corrected for selection effects and redshift distortions. It is confirmed through gravity, in weak lensing profiles that show a real mass deficit and a surrounding ridge. It is described through flow, in coherent outward motions that reveal how the low-density interior feeds the denser web. It is connected to light, in small lensing and microwave imprints that turn a missing mass into a measurable influence on photons. In the quiet ecology of a void, galaxies grow with fewer disruptions, retaining disks and gas more often than galaxies in crowded environments, while also living with thinner supply networks and weaker external pressure. In the broader cosmological role, voids become tools. Their statistics reflect the growth of structure and the expansion history. Their shapes and redshift space anisotropies test geometry and dynamics together. Their lensing and microwave signatures link matter distributions to evolving gravitational potentials. No single void carries the whole story. Each is one basin in a continuous landscape. Yet taken together, voids occupy most of the universe's volume, and their regularity in large samples makes them reliable. Future surveys widen the mapped volume and deepen the tracer field, turning void catalogues into sharper instruments and reducing the dependence of conclusions on any one definition or any one data set. The emptiest regions then become not a blankness to ignore, but a calm place where the universe's rules can be read with fewer complications, and where the absence of matter becomes one of the clearest measurements of how matter and space evolve together.